Hey everyone, I wanted to do a quick video of ionic compound Lewis dot structures. In today's video, this lesson here, whenever we're given a metal and a non-metal element, we know those form ionic compounds, but we want to be able to write the Lewis dot structure. We'll learn what that means. The Lewis dot structure of the two elements as they form an ionic compound. All right, so let's look at an example of the formation of a Lewis dot structure. Down here, we have a sample of pure sodium metal. It'll normally kind of look like this, and we'll see that if we cut it fresh, it's this kind of shiny appearance. And if you zoom in microscopically, you see all of these Na atoms just right next to each other, forming these kind of like metallic bonds sticking together. And then if you look at pure chlorine gas, notice it has this yellowish look to it. And if you were to zoom in at the atomic scale, then we'll see that each chlorine atom, it is diatomic, so each one of them is like a Cl2. We see that there's two Cl's kind of overlapping there with the bonding. If these two things react with each other, it's very violent. You'll see like a bunch of black smoke come out of the container, and then the result looks a lot different than the two elements. Here we have table salt, NaCl, and this is held together with ionic bonds, and the sodium now has a plus charge all of a sudden, and the chlorine, it looks bigger than before, and it's kind of split up a bit. Now it has a negative charge, and the resulting compound is, table salt is this crystalline substance that it's not metallic, it's not a gas, it's something totally different, something harmless to eat. So down here, I did want y'all to describe the pure sodium metal and the pure chlorine gas, to describe the sodium chloride structure. And question to ourselves now is, how did the sodium get a positive charge and the chlorine get a negative charge? Like, where did that come from? In this lesson, we'll figure out that the metal actually donates an electron to the non-metal, and that is where those charges come from. So let's look at how to draw this with Lewis dot structures. Before we do this, it's really helpful to be able to draw the ion of each element. So you want to know what the original element looks like, how many protons and electrons there are, and what the Lewis dot structure of that individual element might look like as well. So for example, with potassium, potassium is element number 19. We can look on the periodic table here that potassium is indeed number 19. So that means it has 19 protons and 19 electrons normally. And since it's in the first column, it's probably going to have one valence electron. So that means that we can say, oh yeah, it has 19 protons, 19 electrons. And if we were to draw the Lewis dot structure, which is just a representation of the atom with all of the valence electrons drawn around it, we just have the one dot drawn around it. Whenever a metal like potassium, like an alkali metal, is going to ionize, it's going to lose all of its valence electrons here and have that charge of however many electrons it lost. So in this case, potassium just had one valence electron to lose, so it's going to have a charge of 1 plus. Notice that the dot is no longer there, and we put this plus sign on the picture of the potassium. Since we lost one electron, we also have one less electron in our total count of electrons there. Positive ions are called cations, so make sure that we're calling it that. Looking at this other example, what happens when something like phosphorus is an atom and whenever it ionizes? Well, phosphorus, you want to look that up on the periodic table, is over here. It is number 15, so that means it probably has 15 protons and electrons when it's neutral. And since it's in group 5A, I'm thinking it has 5 valence electrons. So we probably draw 5 dots around it. And then we'll say, hey, it has 15 protons and 15 electrons. Whenever it ionizes, nonmetals tend to gain electrons until they have a full octet, or if they have 8 electrons. So if you have 5 electrons here, you're probably going to gain 3 more electrons to look like you have 8 dots around it in your picture. If you gain 3 electrons, that means you're going to have an additional -3 to your charge. So your charge here is going to be 3 minus. So we tend to draw that somewhere in the top right. We still have 15 protons, but our total number of electrons will now be 18, and this would be considered an anion because anions are negative ions. So I want you to try out these rest of examples on your own, and then continue the video once you feel like you've done it. Check your work. I'm going to work through them quite quickly just to make sure I'm not wasting too much of your time. But without further ado, let's continue. So calcium, this is number 20 on the periodic table, and it's in column 2, so it's going to have 2 valence electrons. So I'd probably draw it something like calcium with 2 dots around it. And then, since I said it was number 20, it has 20 protons and 20 electrons in its neutral state as a metal. When it ionizes, it should lose those 2 electrons and have a 2+ charge, meaning it will have 20 protons and 18 electrons, and that positive charge makes it a cation. Over here on the right, we have bromine. Bromine is number 35 on the periodic table. We see it over here in the nonmetal section. It's also in group 7A, so it probably has 7 valence electrons. So we're going to do 7 dots around bromine. And then we're going to say it has 35 protons and 35 electrons since its atomic number is 35. Bromine, whenever it ionizes, it does want 8 electrons. So we're probably going to gain 1 electron and have a total of 8 dots around this ion in the Lewis dot drawing here. And we'll have a 1- charge in the top right, giving us a total of 35 protons and 36 electrons. The negative charge making this an anion. Over here, aluminum. Aluminum, we learned previously in this class, it's always going to have a 3+ charge, which implies that it has 3 valence electrons to give up. So we're going to draw 3 dots around it. It is element number 13, so we're going to say it has 13 protons and 13 electrons. And when it ionizes, it's going to lose those 3 valence electrons, no more dots around it, and it'll have a 3+ charge. So we still have 13 protons because it's still aluminum, but we only have 10 electrons after the fact. This would be considered a cation since it's positive. Over here we have strontium. Strontium on our periodic table is over here in the second column. Strontium is number 38, and since it's in the second column, it would likely have 2 valence electrons. So let's draw 2 dots around it, and then we're going to say it has those 38 protons and 38 electrons. If it has 2 valence electrons, we're probably going to lose them when we ionize and have a 2+ charge, making that a cation and bringing the total number of electrons down to 36. It should still have 38 protons. Okay, so now we kind of know how things ionize. And we drew what was called the Lewis dot structure of the ion and the Lewis dot structure of just the neutral element before it gains or loses electrons. But we want to be able to draw the combined result of the metal and the nonmetal. So what happens here? Well, when the metal reacts with the nonmetal, electrons are going to be transferred from the metal to the nonmetal. This is because the nonmetal tends to be much more electronegative than the metal, which means it's much more attracted to electrons than the metal is. So the metal is basically like, okay, whatever, take my electrons, and the nonmetal is happy to eat them up until each nonmetal has 8 valence electrons and each metal lost its valence electrons. So let's look at a strategy on how to draw this in action, and then we'll go ahead and solve the rest of these practice problems together. So whenever I look at 2 things that are going to combine, like lithium and chlorine, I believe the best thing to do is to first come up with what the formula is going to be based off of our knowledge of before. So I like to look at each element and think of what they would look like as an ion. So lithium is in column 1A, so it probably have a 1+ charge as an ion. You see that here, right there in the first column. Chlorine is in 7A, so it probably have a 1- charge as an ion. We see here chlorine would probably just gain 1 electron to get 8 total valence electrons. So that tells me you probably just need one of each ion in order for those charges to add up to 0. So this is how we'd write our formula, LiCl, which tells me in whatever drawing I'm going to make, I'm probably just going to have one Li and one Cl. So in these Lewis dot structure drawings of bond formations, what we're going to do is we're going to kind of draw a before and after going on here. So before anything happens, there are no charges. Lithium has one valence electron around it. So we'll say Li with one dot around it. It's kind of a big dot, honestly. And then we'll have Cl over here with 7 valence electrons around it, since it's in column 7a. So we'll do 1, 2, 3, 4, 5, 6, 7. And notice I'm just kind of pairing these up as I go around. That just tends to be how chemists like to draw these, to be neat and tidy. And electrons do like to be bonded in pairs for the most part. Now, we did say that the electrons during this bond formation, they get transferred from the metal to the nonmetal. So we're going to draw that electron moving from the metal to the nonmetal, just kind of filling in that gap there. And after that happens, we have to show the result. So if lithium lost that electron, if it donated that electron to the chlorine, now it doesn't have it. It just has a plus charge. And chlorine, if it gains that electron, it's going to have 8 dots around it instead of 7. And it'll have a 1 minus charge. So this result, this is the ionic compound. The ionic compound is just filled up with a bunch of these alternating Li pluses and Cl minuses, and they're held together by like this plus charge, which is attracted to the minus charge. So this is a compound, and these are the elements forming the compound. And this is our before and after. Okay, if you're feeling confident in this already, go ahead and try to solve the rest of these, and I will solve the rest of them as well. So you maybe pause the video here, try to solve these on your own, and then I will kind of go through the results, working them out. So in this next problem, we have calcium plus bromine. Calcium's in column 2A, so I believe it'll have a 2 plus charge. Bromine is in column 7A, so those tend to have a 1 minus charge. Whenever I look at Ca with a 2 plus charge and Br with the 1 minus charge, I'm thinking you need 2 of these bromines to cancel out the charge of Ca. So the formula is probably going to be CaBr2. The reason why I wrote this formula is because this tells me in my drawing I'm going to have a single Ca and I'm going to have 2 Brs. So let's draw a before and after of that. I have a single Ca and 2 Brs, and I'll have an after as well. So I'll do a single Ca and 2 Brs. And this is like the before and after arrow. So before anything happens, I know that calcium's in column 2A of my periodic table. So I'm going to say there's 2 dots around it. And I know bromine is in column 7A, so it's probably going to have 7 dots around it each. And I kind of like to leave the blank spot on the left side here, because I know that this calcium is going to donate this electron to the bromine. Each bromine only really wants 1 electron, so notice here that I just show that calcium is going to give 1 electron to the first bromine and 1 electron to the second bromine down there. Okay, after that happens, calcium doesn't have those valence electrons anymore, so it will have a 2 plus charge, and it will actually be a smaller ion as well. Just like, maybe it would have been this size with the electrons before, maybe it's going to be like a little smaller after the fact. And then each bromine will have 1 more electron than before. So if you have an extra electron compared to before, you're going to have a minus charge. And in your ionic compound, you'll have kind of alternating sequence of calcium with 2 plus charges being attracted to 2 bromines with 1 minus charges. And notice the bromines have 8 dots around them each. Okay, let's look at the next example. Here we have magnesium and oxygen. Magnesium is in column 2A of our periodic table, so it will have a 2 plus charge when it ionizes. Oxygen is in column 6A, so it'll have a 2 minus charge when it ionizes. It's just 2 spaces away from your noble gases, and it's in 6A, so when it gains electrons, it will gain 2 of them. And since you just need, 2 plus cancels out 2 minus, I'll probably just do one of each in the formula. And when I'm drawing my before and after here of these, I'm going to say magnesium has 2 dots around it since it was in 2A. Oxygen has 6 dots around it since it was in 6A with the periodic table. And the magnesium is going to give both of these valence electrons to oxygen because oxygen wants to have 8 valence electrons total. So after that happens, magnesium is going to have a 2 plus charge and no outermost valence electrons there. And then oxygen will have 8 dots around it. And since it gained 2 electrons, it'll have that 2 minus charge. And this bond is held together by these opposite charges. In this next example, we have sodium and phosphorus. Sodium's in column 1A, so it'll have a 1 plus charge. Phosphorus is in column 5A, so it'll have a 3 minus charge. I'm thinking you probably need an Na3P for these things to cancel each other out. You need 3 of these 1 plus charges to cancel out a 3 minus charge. So that's where we got this formula from. Which means in our picture, we'll probably have 3 sodiums and a single phosphorus. So I'll kind of draw the before and after of that. 3 sodiums and a single phosphorus. We want to make sure we have the correct number of dots around each. Each sodium was in column 1A, so it should have 1 valence electron around them. And phosphorus was in column 5A of the periodic table, so it should have 5 dots around it. So each sodium is going to be so generous and give these valence electrons over to phosphorus. 1, 2, 3. We'll draw a little arrow for each electron being transferred. And after that happens, now we have each sodium has a 1 plus charge, and then the phosphorus has 8 total electrons around it with a 3 minus charge. Okay, moving on, we have aluminum plus sulfur. So as we learned earlier, aluminum is going to have a 3 plus charge when it ionizes. Sulfur is going to have a 2 minus charge when it ionizes since it's in column 6A. This is a familiar pattern whenever you have a 3 plus charge and a 2 minus charge. If you're like, how to make these cancel, you can just kind of swap and drop the charges, or you can think of the least common multiple. And the least common multiple is going to be, what is a positive charge that cancels out the negative charge. So the least common multiple between 3 and 2, the smallest number they both can be multiplied into is 6. So if you think about, how many aluminums are going to fit into 6, a charge of 6 plus, then you need 2 aluminum ions. If you think about how many sulfur ions are going to fit into a 6 minus charge, we need 3 of these to fit into there. So we'll have S3. So our formula is going to be Al2S3. So it tells us we're going to have like 5 different atoms in our drawing. So we'll have 2 aluminums, and then we'll have 3 sulfurs. Make sure you're drawing small enough for that. Each aluminum should have 3 dots around it because I know each one of them is going to give up 3 electrons and get a 3 plus charge. And each sulfur should have 6 dots around them because it is in column 6A. All right, and the formation of the ionic bond, the metal should give all of these electrons over, but each sulfur only wants 2 electrons, so make sure you only ever give each sulfur 2 distinct electrons here. And it might look something like that, where each aluminum's giving a sulfur 2 electrons, and then those 2 aluminums give 1 electron to like a middle sulfur. After that happens, each aluminum should now have no dots around it with a 3 plus charge, and each sulfur should now have that octet of electrons. They should each have 8 dots around them with a 2 minus charge each. And if you were to add up all the charges, you'll see that, yes, 2 of these 3 plus charges add up to 6 plus, and that balances out and is attracted to 3 of these 2 minus charges, which add up to 6 minus. Okay, finally, we have potassium and selenium. Potassium's K of a 1 plus charge since it's in column 1A. Selenium is Se. It's a nonmetal in group 6A, so we'll have a 2 minus charge. So the formula is probably going to be K2S because you need 2 plus charges to cancel out a 2 minus charge. And the drawing, would probably look something like this to start out with. You have two Ks and a single S. Each potassium should have a single dot around them, that one valence electron. The sulfur should have 6 valence electrons around it. And each potassium is going to give one of their valence electrons to the sulfur. And after that happens, each potassium no longer has that valence electron. They'll have a 1+ charge. And the sulfur will have 2 extra valence electrons compared to before. It will complete its octet, and it will have a 2- charge. So that's all we really learned in a nutshell. Make sure that you know with ionic compounds, normally it's going to be between a metal and a nonmetal. And due to the difference in electronegativity, those electrons get completely transferred from the metal to the nonmetal. And we want to make sure a nonmetal has 8 valence electrons after that happens, which is called having an octet of electrons. I hope you learned a lot. If you have any questions, please ask me or whoever teacher you have. Thanks for watching.